All right, let's talk about something huge. We're in a race to build a completely new kind of reality using quantum computing. Now, this is a technology that honestly sounds like science fiction. It promises to solve problems that we've always thought were just impossible. So the big questions are, what exactly is it, and how close are we really to harnessing all that power? Let's dive in.
Okay, so to really get why we even need quantum computing, let's start with a bit of a puzzle. Think about it. We have these incredible supercomputers, right? Machines that can just crunch billions of calculations every single second. So why can't they solve some of our absolute biggest problems? I'm talking about things like designing life-saving medicines from scratch or making global finance truly secure. Why are those challenges still completely beyond their grasp?
Well, the answer, in one word, is complexity. You see, for certain types of problems, the number of possible solutions just explodes. It grows exponentially. Imagine you're trying to design a perfect new drug molecule, or maybe figure out the most efficient route for an entire global supply chain. A regular classical computer has to do it the slow way, check every single possibility, one after another. And pretty soon, that task would literally take longer than the age of the universe. They just slam into a fundamental computational wall.
So here's our game plan. First, we're going to look at that classical wall and why it's such a big deal. Then we'll get into the quantum difference, the seriously weird physics that lets us smash right through it. We'll also cover how these things are actually built, separate the promise from the reality of where we are today, and this is the cool part, how we can start putting quantum ideas to work right now.
All right, section 1, that classical wall. So let's really dig into this. Picture this. You're planning a huge military mission, and there are thousands of moving parts, thousands of variables. Or maybe you're trying to engineer a brand new aerospace material, atom by atom. A classical computer, well, it has to look at every single combination, one at a time. And as you add just one more variable, the number of possibilities doesn't just grow, it explodes. The computer just runs out of steam. It runs out of time and power. It is purely a problem of scale.
So to get around that wall, you can't just build a faster version of what we already have. You need a whole new way of thinking about information. You know, a classical computer uses bits, and a bit is basically a light switch. It's either off, that's a 0, or it's on, a 1. Simple. But a quantum bit, a qubit, that's more like a dimmer dial. It can be 0, it can be 1, or it can be a mix of both at the same time. And that single ability, the power to hold all those possibilities at once and explore all those paths in parallel, that is the secret sauce. That's where all the power comes from.
And that idea, that's what brings us to the quantum difference. We are literally leaving the world of simple on or off logic behind. We're stepping into the very strange, almost magical world of quantum mechanics. And it completely rewrites the rulebook for computation.
So, the first big idea you have to wrap your head around is called superposition. This really is that dimmer dial concept we just talked about. A single qubit can be a blend of both 0 and 1. Because of that, a whole system of these qubits can hold a ridiculous number of possibilities all at the same time. And that's the game changer. It lets a quantum computer survey this vast landscape of potential answers all at once, instead of trudging through them one by one.
Okay, if you thought that was weird, the next principle is even stranger. It's called entanglement. You know, Einstein himself called this spooky action at a distance, and for good reason. When you entangle two qubits, their fates are, well, they're linked. If you measure the state of one, you instantly know the state of the other one, even if it's on the other side of the galaxy. It's this bizarre, spooky connection that lets all the qubits work together as one incredibly powerful, unified system.
Now, here's where it gets really crazy. When you put superposition and entanglement together, the power doesn't just add up, it multiplies. It scales exponentially. And this is the part that is just truly mind-boggling. Get this. With just 300 perfectly entangled qubits, a quantum computer could represent more states than there are atoms in the entire known universe. Just let that sink in for a second. That is the kind of staggering, astronomical, computational space we are talking about.
Okay, so the theory is absolutely wild, but how on earth do you actually build one of these things? Let's move away from the abstract physics and get down to the nuts and bolts, the actual hardware.
Yeah, it turns out there's no single recipe for building a qubit. It's more like a race, with different teams trying completely different approaches. You've got giants like Google and IBM using these tiny superconducting circuits, which have to be kept colder than deep space. I mean, unbelievably cold. Then you have companies like IonQ that are trapping single ions with lasers. And there are even newer ideas, like the work at Caltech, using grids of neutral atoms. Every single one of these methods has its own strengths and weaknesses, and honestly, we don't know yet which one's going to win out. So what does it actually look like to run a program on one of these? Well, you can think of it kind of like a four-step dance. First, you get all your qubits lined up in a starting position. Step 2, you hit them with these super precise pulses, they're called quantum gates, to nudge them into that complex dance of superposition and entanglement. That's where the real magic happens. Step 3, you measure the result. The moment you look, the whole quantum state collapses back down to a simple, classical answer of zeros and ones. And because there's some chance involved, you usually have to run the dance a bunch of times to see which answer pops up most often. That's your most probable correct solution.
All right, so far this all sounds pretty amazing, right? But now it is time for a serious reality check. Because for all the incredible promise, we got to be honest about where this technology is today. It's not magic, and believe me, it is far from perfect.
Right now, we're living in what all the experts call the NISQ era. NISQ. It stands for Noisy Intermediate Scale Quantum. So intermediate scale is pretty straightforward. It just means our machines have, dozens or maybe a few thousand qubits. That's a long way from the millions we'll eventually need. But that first word, noisy, that is the most important word you need to remember.
So what does noisy actually mean? Well, it boils down to 3 huge challenges. First up, error rates are just really high. Even a basic operation can easily go wrong. Second, these qubits are unbelievably fragile. I mean, the tiniest vibration or temperature change can make them lose their special quantum properties. That's called decoherence. And poof, your calculation is ruined. And finally, on a lot of the chips we have today, not all the qubits can even talk to each other directly, which really limits the complexity of the problems you can throw at them.
But here's the thing. Even with all those challenges, the momentum behind this field is just undeniable. I mean, just look at the money pouring in. In the first quarter of 2025 alone, more than $1.25 billion was invested into quantum. That's more than double the investment for the entire previous year. This isn't just a trickle, it's a flood of cash and brainpower, and it is pushing progress forward at an absolutely incredible speed.
And all that acceleration means something really important. We don't have to sit around and wait for some perfect, magical quantum computer to appear. We can actually start getting value from these ideas today. So let's talk about that. How can we put quantum to work right now on real-world problems?
Now, let's be clear, a quantum computer is never going to replace your laptop for sending emails or watching videos. It's not for that. It's a highly specialized tool for a certain class of brutally hard problems. Think about things like optimization, like finding the one single absolute best route for an entire global shipping fleet, or simulation, where you can model a new drug or material down to the individual atoms. And of course, it's set to completely change the game in cryptography and some very specific areas of machine learning.
And this, right here, might be the most practical thing you hear today. You don't actually need access to a quantum computer to get in on the action. See, clever researchers have developed what they call quantum-inspired algorithms. These are brilliant techniques that borrow the logic of quantum computing, but run on the classical computers we already have. And for the right kind of problem, they can give you a massive performance boost, sometimes up to 20 times faster, today.
So, what does this all mean for you or for your company? It's simple. The time to get ready is now. Not tomorrow, not next year. Now. You should be identifying the really high-value, super complex problems in your industry. You need to start training your engineers and scientists to think in these new quantum ways. Because let me tell you, the organizations that start building that muscle now, finding the right problems, training their people, running small pilot projects, they're the ones who are going to have a massive, decisive head start when the hardware finally matures.
And that brings us to the big final question, doesn't it? As this technology rockets forward, what's the end game? Is quantum computing going to be the key, the revolutionary engine that finally solves humanity's biggest, gnarliest problems? Things like climate change, curing diseases, you name it? Or is it going to be a phenomenally powerful but ultimately very specialized tool for just a handful of specific tasks? We don't know the answer yet, but the race to find out is absolutely on.